All right, so we started covering pointers last time, and we're going to do a little bit of a review and then move on to why you want to use pointers. Again, a pointer, remember, is a memory address. Sometimes we call them references. A pointer can be declared using the star syntax. So if I want to create an integer pointer, it would be int star p. By the way, if it wanted to have a pointer that points to a double, I would use double star p, right? Your pointers should match the types that they're pointing to, because if not, then you're pointing to a different amount of memory. Remember that an integer is only 4 bytes. A double is 8 bytes. So if you create a pointer to an integer, 4 bytes, but then you're pointing to a double, you're pointing to only half of the data, right? And so it'll be weird results and nothing that is interpretable, right? It's always best practice to initialize them to null when you declare them, so that that they're not pointing to some random memory location, right? To make a pointer, take a pointer and turn it into a regular old variable. In order to assign a value to it, you can use the star operator again. In this case, it's not the star syntax, but an operator that dereferences it, right? To make a regular variable into a pointer variable so that you can get the memory address of that variable, that would be the ampersand, right? So the star and this ampersand. And the takeaway from last time is that don't make pointers point to things that they shouldn't point to, right? If they point to things that they shouldn't point to, then you're going to get a segmentation fault, hopefully. In the best case scenario, you'd get a segmentation fault. Right? So as a reminder, let's go ahead and come over here to Python Tutor and walk through that one more time with a different visualization. I'm going to go ahead and create a regular old variable and set it equal to 42. Then I'm going to create a pointer variable, star p, right? And I'm not going to set it initially to anything. Right? So what is it pointing to at this point? Who knows? It could be anything. Random memory location, dead beef, whatever. Let's make it point to null so that it's safe. It's safer, right? Now let's go ahead and make it point to something that is valid. I will make p point to a, except that that's not the way to do it, remember? The thing on the left-hand side is a pointer. The thing on the right-hand side is a regular old variable. I need to make them match. Now I could do this. Right? I could dereference p and then set it equal to whatever the 42 in this case. But what is p pointing to before I even got there? Null. And what did Bret Hart say? Don't dereference a null pointer. Right? So that's not the way to do it. I need to make the other side match. Ampersand changes a regular old variable into a pointer variable. And now I can change the value pointed to in p. I can make it equal to 43. Is that one correct? No. Why? What is this doing? It's making p point to memory address 43, which doesn't belong to us, may not exist, etc., etc. So what do I need to do to make the left-hand side now correct? Dereference it with a star operator. Once again, let's go ahead and visualize this execution. I showed you pictures of this yesterday, but they were static pictures. Now we can walk through it and actually see what's going on. I've got my stack up here with A and P. Right now, they've not been initialized, so they're big question marks. So, 42. What is P pointing to still? Question mark. It could be anything. When I set it to null, though, now it's pointing to null. Null is not a real memory address. If you try to dereference it, it's dereferencing a null pointer. If you try to work with it, it's not going to work. It's going to give you a segmentation fault. So we'll now make P point to A. Do you see what's going on there? We've now got an actual arrow up here. Now I consider it a bug, but you can take this arrow and I think you can move it around. Yeah, you can move this around and screw around with it, but it won't actually change your program or anything. It just makes it disappear. So let me go ahead and rerun that. Visualize this. And next. There we go. Now I'm going to dereference P and set it equal to 43. What that is doing is it's starting at this pointer, it's jumping to that memory location, and it's going to treat it like a regular old variable so that 42 now becomes 43. All right? So that is the basics of pointers. Now remember, and I always liken this to when I took calc many years ago. I could never remember which one was the negative one, which one was the positive when I took the derivative of sine and cosine. The derivative of sine is positive cosine. The derivative of cosine is negative sine. And so I put that up on a Post-it note, and this many years ago, I still forget what it is. All right, so ultimately what you're going to have to do is just put this up on a Post-it note to remember when do you use star and when do you use ampersand, right? Oops, sorry. I meant to copy paste that. All right, there we go. A regular old variable, changing that into a pointer variable, you use the ampersand. If you've got a pointer variable, changing that into a regular old variable, you use the star operator. Right? So those are just two things that you're going to have to remember. You don't have to commit it to memory, but you'll get used to using it so often that you will it will commit to your memory at some point. Right? All right. So what we can? Yep, we got good. We've got audio. We can always change regular old variables anyway, right? I could have just set a equal to 42. Why the hell do I need these pointer things, right? For that, I'm going to remind you about the swap demonstration over here. Right? Remember, if I create two variables here, a is equal to 10 and int b is equal to 20, right? And then I print them out. Printf a is equal to %d, b is equal to %d, and the line, a, b. And I call that swap function. Did it work when we tried this before? No, because it is passed by value, right? Copies of a and b are provided to the swap function over here. But now what I'm going to do is I'm going to change the swap function. I'm going to write a different swap function that doesn't use pass by value. It uses pass by reference. In other words, we're not going to give it a and b, two values. We're going to give it a and b, two pointers, memory locations. So let me go ahead and create a new function here, swap by reference. Right? And if it was like a and b before, then it's no different. Right? What I'm going to do is I'm going to change these into pointers. Now, how do I make this into a pointer? How do I declare a pointer? Star. Make that into a star as well. Right? Now, I am passing in pointers to a and b. If I've got pointers to a and b, what can I do? I can dereference them and jump to that memory location. Dereference and jump to that memory location, and I can swap the actual contents of memory now. How do we do that? Well, let me grab this code, right? And let's try it. Let's go ahead and change this now. All right, so the thing on the left-hand side is a regular old variable. The thing on the right-hand side, however, now is a pointer. So how do I take that pointer and change it into a regular old variable? Star. Star, star, and star. By the way, do I do temp? No. At that point, temp would have the value of 10, so you're jumping to memory location 10, and that doesn't make any sense, right? Okay. All right. I want to call that function now instead of the swap function over here, all right? But remember, what is swap by reference taking now? It's taking two pointers. Are a and b in the context of main, are those pointers? Nope. How do I take that regular old variable and change it into a pointer variable? Ampersand. Ampersand. Right. Now let's go ahead and just watch it, and then we'll take a look at a visualization of it. GCC wall flag, or I'll do a demo.c wall. There we go. No warnings is good. Let's go ahead and run it. Now remember, before when it was passed by value, it was 1020 and 1020. It was unaffected. But now, it's 1020, 2010. Once again, let's go ahead and look at this from the visualizer. All right. Get rid of all that and visualize this. Okay, fine. We don't have utils here. And visualize that. All right. So let's walk through this now. 10 and 20. They get initialized. They get printed out, and you've got 10 and 20 up here. Okay. Now I'm going to jump into that function. And when we jump into the function, you'll see over here the stack. A brand new stack frame is created, right, for swap by reference. It takes two pointers, a and b. Note that they are not integers. They are a pointer to an int. Whereas up here, they were actually integers. Okay. And then temp is just a regular old integer. I will go ahead and jump to those memory locations. grab the memory location at the values located at memory location A and place it into the temporary variable right here. And then I will jump to the memory location A and set it equal to whatever is in the memory location B, right? And likewise for B. And did you see them get swapped up here? Right. Now, if I had swapped the pointers, right, they would change what they're pointing to, and that would have had no effect, just like the original pass by value version of this would have been. Okay. Jump again, and now that that stack frame is destroyed, and we see that we've got 10 and 20. Okay. So again, passing by reference. When you've got pass by value, then copies of the variables are passed to that function. Pass by reference means that the memory address, i.e. the pointers or the references of the variables, are passed to the function instead of copies. Right? That way you can now manipulate the values, because you have the original values, I should say, the original values, because you have access to their memory locations. You can jump to those memory locations and you can do whatever you want with them, right? Now, once again, with great power comes great responsibility. You actually have you have access to the raw metal, so we say, meaning that you have access to the actual memory contents and you can manipulate those. Well, again, what happens when you do something illegal? You try to dereference a null pointer, or you try to work with memory that doesn't belong to you. Segmentation faults occur. Okay, and hopefully a good operating system would not allow that. A bad operating system, one that you can then exploit, would allow that, and now you can have a program access memory that it shouldn't have access to. Right? But another thing is now allowing us to return multiple values from a function. Now, what do I mean by that? Think about yesterday's lab. You wanted to convert an RGB value, red, green, and blue, into a sepia tone. Right? You had to do it with 3 functions. 2 sepia red, 2 sepia green, 2 sepia blue. What if you could do that with one function by returning 3 values? Now remember, a function can't return more than one value. That's not mathematically correct. But we can do it if we have pass by reference values. Let me show you. Right? So let me come over here to utils, and we'll use a different example. Do you remember that we did, maybe we did it functions, maybe we just did it directly to compute the quadratic roots, get root 0, 1 of double A, B, double B, double C, right? And that's the first root, negative b plus minus square root of 4, square root of b squared minus 4ac, et cetera, et cetera, et cetera, right? There's one of those where it's plus, and then there's the other one that is minus. So you'd have to have 2 functions here because you need to have 2 values from it. Right? What would that look like? I mean, basically you would be repeating the code over at least twice here, right? What's the first root? Remind me of what is the quadratic formula again? Negative b plus square root, not minus will be the other one. Plus minus, then b squared minus 4ac all over 2a. I need to make sure that the numerator is collected though. There we go. All right. Is that one good? All right. Then what about this one? We just copy pasted code and now have a minus. Okay. I have to have 2 functions to do this though. One of them called getRoot01 and getRoot02. Let's think of what it would look like now that we've got a pass by reference way of doing things. All right. So what I'll do, I'll call this compute roots, both of them. All right. You still need the coefficients a, b, and c. Okay. But now what I'm going to do is I'm going to pass 2 what I like to call buckets. I'm going to give you 2 buckets. You're going to put the first root in the first bucket and the second root into the second bucket. Those buckets are going to be double star root 1 and double star root 2. Both of them are passed by reference variables that I can then set. I can fill those buckets up with the 2 values. And because we're sharing those buckets, I can return 2 values now. just like you're going to do next week in your lab when you're going to return 3 values, an R, red, green, and blue value. Right? All right, what does it look like? Well, do I need to return type anymore? I'm not actually returning anything, so void. We'll come back to that because now we can actually use that for something else and make it even more useful. All right? Now, what does it look like? I don't return the first root. Instead, I set the first root. So root 1 is equal to this. Does that look right? No, doesn't look right to me either. Let's find out why. I'll cut and paste this, cut and paste that. And then remember that I'm not returning anything, so just return. Really quick review here. How do I compile just the utils file? gcc utils.c. What flag do I need to use? Hyphen C for compile. Hyphen O would say, I want to create this output file. And, by default, it'll create utils.o. Uh-oh, there's a problem there. Wow, it's an entire error. Okay, great job. Root 1 and root 2. So wow, I can't, that should be a warning, but all right, fine. That's a good job, GCC. That is an error. What is wrong with it? I asked, is that right? And you said no. The thing on the right-hand side is a number. The thing on the left-hand side is a what? An address, a pointer, a reference. So how do I take a pointer variable and make it into a regular old variable so I can set it? Star. Right? And now that error should go away. And it does. Always compile, even with the wall flag, just to make sure. Right? All right, now let's go ahead and actually use this. I'll get rid of this swap stuff here. Right? And let's say double A is equal to 10, double B is equal to 20, double C is equal to 10. I want B to be large so I don't get complex roots. Now let's go ahead and call that function, which I called compute roots. And I will pass in A, B, and C. Well, what about my return values here? My return values. They're not being returned, but instead they are being passed by reference. I now need variables for them. So here's my first attempt. Double R1. That's a pointer variable, right? Yeah. Double R2 with a star in front of it. That's a pointer variable too. If I were to pass these in, R1, R2, the compiler is just fine with this. Utils.o and demo.c. I'll even turn on all the warnings, and you'll see that after I get the -lm flag there. All right. Oh, wow. All right. Good. Quiet you. There. I didn't mean for it to turn on those warnings, but it clearly is something wrong here. What was so ignore what it actually told you, and we'll read that again in a second here. What is wrong with these two pointer variables?
You're making the pointer in the function point to a pointer.
Well, okay, so I'll simplify the question. What is R1 pointing to right now? Nothing. Can I then, if it's pointing to dead beef or null or something like that, can I go to that memory location to fill that bucket with one of the two roots? No. So, no and no. Okay? Now when I compile this, hopefully the warnings will say, wait a second, these are pointers, but you're passing in regular old variables. So R1 and R2 are now regular old variables. How do I change those into pointer variables? Ampersand and ampersand. There we go. Now we can go ahead and do that. Right? And the okay, let me go ahead and we can restore it really quick and take a look at the error message, or the warning message, I should say. There we go. All right, and then I have to turn on all the warnings. There we go. What is it warning me about? R1 is an uninitialized value. Dead beef. Question mark. Null. Right? Are you absolutely sure that you meant to do this? Probably not. Right? So let's go ahead and fix it like we fixed it already. Regular variables, now those are stored in memory. Those are valid. Get the memory address of them to pass it to the function. Let's actually go ahead and print it out to make sure it's correct. Printf roots are going to be %f and %f and the line, and R1 and R2. Why don't I provide ampersands there? because they're regular old variables. That's what we do with printf, right? Let's try to compile it again. A.out. And that's correct. If you go to Wolfram Alpha, what are the roots of this? It's going to be -1 and -1, right? Or plug and chug and do it yourself. Okay. All right, great. So we can return multiple values now, right? Like you'll be doing next week with red, green, and blue. Okay. This is now a void function because we're not actually returning anything, right? So I'll ask you, what could go wrong in this function? We've already seen a couple of things that could go wrong. What's one thing that could go wrong here? Well, here, let me come over here. What's going to go wrong if I make this into 1? TCC. Nan and nan. Why are they not a numbers? Because those are complex roots. So now let's go ahead and protect ourselves against that. If it's a complex root, well, how do I do that? If this thing is negative, if that's negative, oops, then error, complex root. That's not real code, right? We'll figure out how to deal with this in a second. Is there anything else that could go wrong here? All right, 0, what could be 0? At the bottom, so A could be 0. Else if A is 0. Now, why would you end up dividing by 0? What if the coefficient, let's do open up Wolfram Alpha over here. What if you have a coefficient in a quadratic equation of 0 on x squared? Is that a quadratic equation? No, what is it? It's a linear equation, right? So this is error, divide by 0, linear equation. We still know how to solve those. We just need to do something else to solve it, okay? Is there anything else that could go wrong? What would Bret Hart tell you? It's right there, guys. You're dereferencing a null pointer. What could be null here? Can A, B, or C be null? No, because those are numbers. They're not pointers. Can root be root 1 be null? Yep. So if root 1 is null, equals null, I can do null pointer checks now, just like we did when we started out here. Or if root 2 is null, that's also an error, right? So error, null pointer, right? Okay. So now first of all, I'm going to clean this up a little bit. Null pointer checks should be the very first thing you do always, period, right? There is no point in looking at anything else if you know that if you keep going, there's going to be a segmentation fault. So what I'm going to do is I'm going to move this thing up to the very top. That's the very first thing I should do, right? Otherwise, none of these errors occur. We can go ahead and proceed and compute this and be done with it, right? Now, what about these errors here? How do I communicate back to the calling function that something went wrong? We've been doing that over in our main for a while now. If you don't give me the correct number of command line arguments, I issue an error message and I exit with an error code. 1, something happened. 2, something else happened. 3, something else happened, right? Then at the very bottom, if everything goes right, what happens then? 0. Nothing bad happened. It's like asking a question, was there an error? False. The only thing that is false is 0. Otherwise, true, an error of type 1 happened. True, an error of type 2 happened. True, an error of type 3 happened. Right? So what we're going to do is we're going to change our function here to do error handling. I will return an integer now. Right? And in this event, if there's a null pointer error, I'll return, I'll mash my keyboard, 432. Right? Otherwise, if it's a complex root error, I will return another mashed keyboard value there. Right? Otherwise, if it's a divide by 0 error, I'll return another different mashed keyboard value there. Otherwise, at the very end, if nothing bad happened, I should return what? 0. Okay? That's communicating an error back to the calling function, the demo function. We can now capture that value. Int error code is equal to compute roots. Now, instead of printing out roots that say nan, not a number, not a number, I can check that error code. If the error code was equal to whatever the error code was for null pointers, null pointer error, question mark, then I'll just simply print out printf, bad memory error. And then I'll move on with the program, right? Otherwise, if the error code is equal to, else if the error code is equal to that other thing, what was the another error that we could occur? The divide by zero error, right? Then I can actually do something interesting here. Right? How would you solve a linear equation? Right? This is equal to 0. This part goes away. How do you solve that? I forgot my x here, sorry. Subtract c and divide by b. So we can say printf, that's a linear equation, man. But the solution is %f anyway. Right. And then what's the solution? Negative c divided by b. Do I have to worry about integer truncation there? Nope, they're all doubles. Right? Do I have to worry about something else though? Yeah, 0. Right? What happens in that case? Now this one goes away. C is always equal to 0, right? There is nothing to solve, right? So I won't worry about that, okay? Else if the error code equals, what was the other part? Complex root error of some sort, right? Then I'll say, I'll just have another message here, printf, I've not learned complex roots yet. So, in any case, otherwise, we'll go ahead and print the roots for you because no error occurred and we're all good. Right? Here, we've got to recompile from scratch here. GCC, okay, that's way too far back. I'll just do it from scratch.
You'll have to put in what the error codes are.
Good thinking here, right? Utils.c, oops. I forgot to change that to an int, right? There we go. So nothing bad is going on with the utils.c, but you're right. This is not real code right here, right? All right, from memory, what was the error code for a null pointer? What was it? Oh, 432. Okay, 432, like that. Maybe. All right. What was the error code for divide by 0? Does anybody remember? 3824. Oh, 3824. Wow, you're really good. You're screwing up my demo, man. You got a good memory. What? 3829. Wow. All right, you got good memories. All right. Come back a month from now. Are you going to remember that? No. Is there a better way? All right. In fact, what are these things called again? They're just random numbers that I was mashing my keyboard with. Right? They are magic numbers. Where the hell did I come up with that? Right? Even if I had used something more sensible like 1, 2, and 3, come back a month from now, are you going to remember, oh yeah, 1 was null pointer, 2 was this, and 3 was that? No. You're never going to remember that. Right? So here's my first solution. Right? We're going to go over here to the H. Right? Remember, I've got these defines. Define. Right? Null pointer error. Now, it doesn't really matter what I set this to. I'll just go ahead and do it 1. Right? Define. What was the other one? Divide by 0 error. That'll be 2. They've got to be unique. Right? And then finally define complex root error. I'll say that that's 3. Right? Now I don't need to play around with those numbers at all anymore. Right? What did I call? Let's see. What did I call a null pointer error? Null pointer error. What did I call complex root error? I called it something readable. Complex root error. Right? And what did I call divide by 0 error? Divide by 0 error. Is that what I called it actually? Divide by 0 error. And I didn't even go in the correct order there. Right? There we go. Now over here, I don't have to remember those numbers anymore. Right? I've not learned complex roots, so no, that's not it. There we go. This is complex root error. and then this one would be null pointer error. That is way more readable, right? I mean, it's human readable now. It's not just some random keyboard mashed number that you can come up with, right? It's an actual human readable title for each one of those types of errors. Now I can actually compile this. So let's go ahead and do that. GCC, compile that, and then compile everything together. There we go, and run it. And I've not yet learned complex roots. Right? Let's go ahead and restore that to 20 to make it sure it works. Let's go ahead and test the other one. Divide by 0. GCC that. Note that I didn't have to recompile the utils file because I didn't change any code in the utils file. Right? That's a linear equation, man, but the solution is negative 0.5 anyway. Is that true? 20x is plus 10. Yeah, that's right. Right. And then finally, I'd really have to try hard to screw that up, but and it's going to warn me about it anyway. But when I run it, nope, bad memory error. Right. Okay. So ampersand R2. All right. Now you might be thinking, well, okay, you can check for null pointers, right? It would be really nice if I could check to see if the pointer is not necessarily null. It's just pointing to something that doesn't belong to me, say 42. Right? That's not null. Right? That's might be a valid memory location. It might be an invalid memory location, but probably with 99.99% certainty, there's no way that it belongs to me. Right? And warning about it, but at the end of the day, oops, let's go ahead and restore that to 10. There we go. Then recompile this. All right. It's still going to be a segmentation fault. Believe me, I would love nothing more than to be able to write code that checks to see, am I about to use memory that doesn't belong to me? If so, I won't do that and I'll do something else. There's no way you can do it in C. Right? You would have to go down one level to the operating system level to and then change how the operating system operates in order to check for that all the time. And that's not something that's compatible with the philosophy of C. The philosophy of C is we give you total power because we want it to be efficient. We want it to be fast. Right? If you start adding in all of those extra checks, now you have a programming language like Java that has automated memory management. Now you have an interpreted language like Python, and you pay a huge price in performance for all of that stuff. Right? C, the philosophy is we assume that you know what you're doing, and we're going to let you do it. And if you don't know what you're doing, then that's your problem, and that's your fault. All right? We're going to let you do it. Right? So there is no way to check for that other than writing correct code to begin with. Right? Later on, if you don't write correct code, then you'll need this other tool called a debugger to find out where the problem is, and we'll cover that later on, all right, after we've done error handling and arrays. But this is your basic introduction to error handling. We'll do more error handling on Friday. That's all I wanted to do today. And so we'll do this again, but more formally on how to do it. And then an alternative, instead of using defines here, and which is arguably a little bit better way of doing it, using what are called enumerations, enums. Right? So we'll do that on Friday, and maybe some extra exercises or something. But otherwise, see you on Friday.